Good morning, folks. Today I'll go over rational functions for the college algebra class. So at the basic level, what do we mean by a rational function? Any function f of x of the form p of x divided by q of x is called a rational function if these two p and q, these are simply polynomials. So polynomials, what do we mean? The exponents are positive integers. The exponents of x are positive integers. So I can give you a basic example. Look at this one. F of x equals, let's say, 2x squared plus 5 divided by x minus 3. This is an example of a rational function, and just one natural question: how do we find the domain of a rational function? So you simply set the denominator equal to 0 and exclude all the values that makes denominator 0. So I set x minus 3 equals 0. So x equals 3. So we need to exclude this one. Because as you know, when you have a fraction of the form a over b, this denominator b should be different than 0. So that's why we have this kind of restriction that you cannot plug in 3 into this function. It's going to be undefined. So the domain of f will be all real numbers except the number 3. So in interval notation, you start from negative infinity and go up to 3. Parentheses, 3 is not included. Union, you start at 3 and go to infinity as well. So that way you're taking that 3 out, because 3 divides your number line into two kind of identical pieces. One starts from negative infinity, goes up to 3, and then the next part starts at 3 and goes up to infinity. So this is just one example, and like I can put another extra example. If you look at this one, like consider this function, which is let's say this time it's g of x equals to 5x squared plus 4 divided by square root of x plus 3. As you see, this is the bottom, the denominator. This is not a polynomial. Not a polynomial, because we have here we have x to the 1/2. X to the 1/2 means the exponent is not a positive integer, so that means the denominator is not a polynomial. So this implements the fact that g is not a rational function. So that's an example of a function which is not rational. And then the next part that I'll talk about is the asymptotes. They're really interesting, nice functions. The rational functions, they have vertical and horizontal asymptotes. Just one horizontal asymptote, and you may have like multiple vertical asymptotes. So I put this example here. It's the function x plus 1 divided by x minus 3. You see it's not defined at 3. And this line, the dashed line, vertical line, is the line x equals 3, passes through 3. And the horizontal one is the one that passes through 1. So it's like y equals 1. So as you look at the graph, first, let's look at the horizontal asymptotes. Horizontal asymptotes. I'm going to write this down as HA. So the horizontal asymptote is a horizontal line that your function comes close to at the infinity side on the x-axis or the negative infinity side on the x-axis. So it's kind of like you take x to infinity, walk to this side, like that way. That means x goes to infinity, and in that case your function comes close to y equals 1. So y equals 1 becomes a horizontal asymptote. So we can just see that if x goes to infinity, then f of x goes to 1. You may think of that as the height. So this is just, I mean, I try to show the horizontal asymptotes on this example. So on the other side, if x goes to negative infinity, if you go to the left side, if you go to this side on the graph, you see the same thing happens. Then f of x goes to 1. If you like, you can also write this as y goes to 1. Or here you can just say again y goes to 1. So if any of these two conditions are satisfied, when x goes to infinity or negative infinity and your function goes to a value, that value becomes a horizontal asymptote. So in this case, we have one horizontal asymptote, which is the line y equals 1. So now you look from a different point of view. Now in this case, in the second case, when we talk about a vertical asymptote, I'm going to write this as VA. In this case, your function comes close to a vertical line when x values are approaching to a value from right or left. Like if you look at this example, if you approach x's to the right of 3, like here to this direction, and look at the y's are going to positive infinity. You see, I just denote it by this way. If x goes to 3 from right, I can just say x approaches to 3 from right. So then you see the f of x or y, these two approaches to infinity, goes just high above. And in the same way, if x approaches to, so it's like 3 from left. So if you approach to now 3 from left on the x values and the function's values are going down, then f of x, or you can just say y, approaches to negative infinity. See, in this case, you're not like in the first case, x values are approaching to infinity or negative infinity. In the second case, x values are approaching to a constant value, constant number, like a number, but the height is going to infinity or negative infinity. So in this case, we just say that this line x equals 3 is a vertical asymptote. That's what we have. So this is how we find the horizontal and the vertical asymptotes on the graph, and it's really pretty straightforward. That you can just think of this way, that your function comes close to but never touches on the right side or on the left side, or when it goes to infinity or negative infinity for the height. Now I'm going to show you one example. Like look at this example on this graph. You will see that one. That see, for example, here, what are the vertical asymptotes? What are the vertical asymptotes? The vertical asymptotes are, see, that's like -2, so that's like -4. It goes with each unit is like length 2. So this is 2, and this is -2. So vertical asymptotes are x equals -2, then x equals 2. Please write them as equations, because they're equations. If you say y equals -2, that's a completely different line. And here, the horizontal line that passes through -4, that's going to be the horizontal asymptote. So the horizontal asymptote for this function is y equals -4. As you can see, the function is not defined at those two values, -2 and 2. So for example, if you look at the domain of this function, it's a natural question. It's going to be negative infinity up to -2. You don't have a value at -2. Can you see your function doesn't touch that vertical line? And the union, it is a piece from -2 up to 2. Union goes from 2 up to infinity. That's how we find the domain, by looking at the graph. So that was an example. Now when you this is when you have this is when you simply have a graph. Now what happens if we have an algebraic expression? If you have an algebraic expression, we have an algebraically given function f of x equals p of x divided by q of x. This needs to be in the simplified form. So you've simplified as much as possible to simplified form. Then the vertical asymptotes can be found by setting the denominator equal to 0. So that's like the values that makes the denominator equal to 0. So those are the vertical asymptotes. So like if that's, for example, k, then it's going to be of the form x equals k. So an example, let me just write down an example. F of x equals to x plus 2 divided by x minus 5. So from here, the vertical asymptote becomes x equals to 5. It's the vertical asymptote. So if you want to find the horizontal asymptotes, now you check the degree of the top and the bottom. If the degree of the top is less than the degree of the bottom, then we have a horizontal asymptote y equals 0. If the degree of the top is greater than the degree of the bottom, then in this case the horizontal asymptote is none. We don't have a horizontal asymptote. And in the last part, if you have the degree of the top equals the degree of the bottom, I'm going to explain this over examples. Then the horizontal asymptote will be y equals the leading coefficient of the top divided by the leading coefficient of the bottom. This is what we have. So now let me just write down some examples about horizontal asymptotes. Let's say f of x equals 3x squared plus 1 divided by 5x to the 4 minus 3. You see now the degree of the top, degree is 2, and then here the degree is 4, highest power of x. So in this case the horizontal asymptote will be y equals 0. If you take another example, let's say g of x equals to 4x squared minus 1 divided by 3x squared plus x minus 1. So see the degree of the top is 2. The degree of the bottom is 2. So in this case the horizontal asymptote will be y equals, you look at the leading coefficient, so 4 and 3, so y equals 4 over 3. That's how we find it. If you look at, let's say, h of x, which is 5x to the 4 minus 3x plus 1 divided by, let's say, 2x plus 4. Now you see the degree of the top is, degree is 4, degree of the bottom is simply 1, first power of x. So in this case we have none, no horizontal asymptotes. So that's how you determine the horizontal asymptotes. For example, for this one, just as an extra, if you want to find the vertical asymptote for this one, you need to set 2x plus 4 equal to 0. So you get 2x equals negative 4. So x needs to be negative 2. That's what we get as the vertical asymptote. That's how we find it. So in this final example, I'll show you how to graph a rational function of this form. Here we go. Here's an example, a basic one. Let's say f of x equals 2x plus 1 divided by x plus 3. So you want to graph this. First, you can find the vertical asymptote. So what's the graph? That's the problem. Try to graph this one. First thing, you can look at the vertical asymptotes. So set x plus 3 equals 0. So we got x equals negative 3. So that's my vertical asymptote. So it's, I can graph that one, x equals negative 3, negative 1, negative 2, negative 3, right here. That's the vertical asymptote, x equals negative 3. And then I'll look at the horizontal asymptote. So degree of the top is 1. Degree is 1. And the bottom has the same degree, degree 1. So you look at the leading coefficients. This is like 1 times x. So then the horizontal asymptote will be y equals 2 over 1. In other words, y equals 2. So let's graph that one. Here we go. Y equals to 2. Now folks, that negative 3x equals negative 3 divides this plane into 2 equal pieces. Right side and the left side. So make a table. Put your function here x, here y equals 2x plus 1 divided by x plus 3. And then figure out some values. From the left side of negative 3, you can choose negative 4 and negative 5. From the right side of negative 3, you can choose negative 1 and negative 2. Then you can plug those points. For example, if I plug in negative 4, it's going to be 2 times negative 4 plus 1 divided by negative 4 plus 3, which is going to be negative 8 plus 1 over negative 1. So it's going to be 7. If you plug in negative 5, it's going to be 2 times negative 5 plus 1 divided by negative 5 plus 3. If you calculate this, it's going to be 4.5. So at negative 4, at negative 5, it's going to be 4.5, somewhere here, negative 5. At negative 4, it is 7. So it's negative 4 comma 7. Then here, negative 5 comma 4.5. So these are the asymptotes. So the function will look like this, folks, on that side. Okay, now on the other side, if you plug in negative 1, it's going to be 2 times negative 1 plus 1 divided by negative 1 plus 3. That's going to be negative 0.5. Top is negative 1, bottom is 2. And then if you plug in negative 2, it's going to be 2 times negative 2 plus 1 divided by negative 2 plus 3. That's going to be negative 3. So at negative 2, its value is negative 2, the value is negative 3. Here we go, negative 2 comma negative 3. And at negative 1, its value is negative 0.5. So it's negative 1 comma negative 0.5. And if you join these, you will get the graph. So it has 2 pieces. You can find the y-intercept. For example, y-intercept will be 1 over 3. You can just check that one. If you plug in 0, you will get 1 over 3. So this is how you graph a rational function of this form. You plot some values, you find the vertical asymptote and the horizontal asymptote, and then you plot them and then graph it accordingly, because those 2 lines are the asymptotes. I hope this video is helpful. Thanks for watching. Bye.